Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. On July 11, 2022, NASA released a single photograph that stopped scientists around the world in their tracks. It showed a tiny patch of sky, an area roughly equivalent to holding a grain of sand at arm's length, packed with thousands of galaxies, some of them so ancient that the light reaching the telescope had been traveling for over 13 billion years. We were looking, in a very literal sense, at the universe as it existed less than a billion years after the Big Bang. That image was taken by the James Webb Space Telescope, the most powerful space observatory ever built, a 21-foot gold-plated mirror folded up inside a rocket and unfolded in space over 1 million miles from Earth. And in the years since that first image, Webb has been steadily rewriting what we thought we knew about the universe, finding things that don't match our models, detecting chemistry we didn't expect, and raising questions that the scientific community is still scrambling to answer. Today, we're walking through what Webb has actually found, the real discoveries, what they mean, and why some of them are genuinely challenging to our existing understanding of how the universe works. In our next episode, we're getting into the conspiracies, claims that Webb's images are computer-generated, that what it's finding is being suppressed, and the theories about what's really out there that NASA isn't telling us. Stick around for that one. Before getting into the discoveries, let's understand what makes Webb fundamentally different from every space telescope that came before it, including Hubble, which it's frequently compared to but is actually a very different kind of instrument. Hubble primarily sees invisible light and ultraviolet, broadly similar to what human eyes can detect. Webb is designed primarily as an infrared telescope, detecting heat radiation at wavelengths longer than visible light. This matters enormously for two reasons. First, the most distant objects in the universe are moving away from us so fast that their light has been stretched, redshifted, from its original wavelengths into the infrared range, meaning Webb can see these ancient distant objects where Hubble could not. Second, infrared light penetrates dust clouds that block visible light completely, allowing Webb to see directly into the stellar nurseries, dense clouds of gas and dust where stars and planets are actively forming, that were previously opaque to optical telescopes. Webb sits at a point in space called L2, roughly 1.5 million kilometers from Earth on the far side of our planet from the Sun. At this location, Earth and the Sun are always in roughly the same direction, allowing Webb's enormous sunshield, roughly the size of a tennis court, to permanently block heat from both the Sun and Earth simultaneously, keeping the telescope's mirror and instruments cooled to within a few degrees of absolute zero. This extreme cooling is essential because Webb is looking for faint infrared signals from the most distant objects in the universe, and any warmth in the telescope itself would swamp those signals with thermal noise. Like, subscribe, and hype the video, because what this telescope found almost immediately after it started operating surprised even the scientists who built it. One of the most significant and most discussed early findings from the James Webb Space Telescope involves something that sounds counterintuitive: galaxies that are too big, too bright, and too mature to exist at the time in the universe's history where Webb is finding them. Our current standard model of cosmology, the framework describing how the universe formed and evolved after the Big Bang, makes specific predictions about how quickly galaxies should have been able to form in the early universe. The model predicts that the very first galaxies should have been small, irregular, and relatively dim, with large, well-structured galaxies taking billions of years to gradually build up through mergers and accretion of material over time. Webb is finding galaxies in the first few 100 million years after the Big Bang that are significantly larger, brighter, and more structurally developed than the standard model predicts should be possible at that epoch. Some of these early galaxies appear to contain stellar masses comparable to galaxies we see in the much more mature, much later universe, suggesting they formed stars at extraordinarily high rates in the very early universe in ways that our models don't fully account for. Cosmologists are actively working to understand this discrepancy. Some argue the standard model needs modification to allow for faster early galaxy formation than previously thought. Others suggest the Webb observations may be revealing limitations in how we measure and interpret certain properties of these very distant objects. But the observations have been independently confirmed and are not going away. Something in our understanding of early galaxy formation appears to need revision. One of Webb's most visually stunning and scientifically rich contributions has been its ability to peer directly into the dense dust clouds where stars and planetary systems are currently forming, regions that were completely opaque to previous telescopes observing invisible light. The now famous Webb image of the Carina Nebula revealed, for the first time in stunning detail, the landscape of an active stellar nursery, a towering cliff of gas and dust with young, newly formed stars emerging from the top of the cloud, their intense radiation and stellar winds physically carving away the material around them and triggering the formation of new stars in the compressed gas below. Structures visible in this image had never been seen before because they had always been hidden behind the dust, invisible to optical telescopes. Beyond the visual impact, Webb's infrared observations of stellar nurseries have allowed scientists to directly observe protoplanetary disks, the spinning disks of gas and dust surrounding young stars where planets are actively forming, in far greater numbers and at far greater distances than was previously possible. Understanding how planets form requires being able to observe them actually forming, and Webb is delivering that observational access at a scale and resolution that represents a genuinely new capability for astronomy. Like, subscribe, and hype the video. And let's get into the discovery that has the most direct implications for one of the biggest questions in science. Perhaps the most directly significant class of discoveries Webb has been making involves the atmospheric chemistry of planets orbiting other stars, and this is where the telescope's capabilities start to connect to one of the most profound questions humanity has ever asked. When an exoplanet passes in front of its host star from Webb's perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching the telescope. Different molecules in the atmosphere absorb light at specific wavelengths, leaving characteristic fingerprints in the spectrum of light that reaches Webb. By analyzing these spectral fingerprints with extraordinary precision, Webb can determine what molecules are present in the atmosphere of a planet hundreds of light years away. In 2023, Webb detected carbon dioxide in the atmosphere of an exoplanet called WSP-39b, the first clear, detailed detection of carbon dioxide in an exoplanet atmosphere. This was a proof of concept rather than a sign of life specifically, but it demonstrated Webb's ability to detect atmospheric chemistry in worlds around other stars with a clarity that no previous telescope had achieved. Subsequent observations have detected water vapor, sulfur dioxide, and other molecules in various exoplanet atmospheres. What makes this capability so significant in the longer term is that Webb will be targeting planets in habitable zones, the right distance from their stars to potentially have liquid water, and searching for molecules like oxygen, methane, and ozone that, if found together in the right combinations, could potentially indicate biological activity. Webb hasn't found those signatures yet, but it has now demonstrated the technical capability to look for them in real exoplanet atmospheres from instruments currently operating in space right now. While much of Webb's attention has been directed at deep space targets, it has also produced remarkable new observations of objects within our own solar system, and some of those observations have turned up surprises of their own. Webb's images of Jupiter revealed the planet's atmospheric dynamics, ring system, and auroras in infrared detail never previously captured from space, including fine structure in the cloud bands and the faint outer rings that hadn't been observed in this way before. Observations of Neptune produced the clearest view of its ring system since the Voyager 2 flyby in 1989, revealing ring structure that ground-based and Hubble observations had only partially captured. More significantly for active science, Webb detected plumes of water vapor erupting from the south polar region of Saturn's moon Enceladus, a moon already known to have a subsurface ocean beneath its icy crust. and found that the plume was ejecting water vapor into space at a rate and over an area significantly larger than previous estimates had suggested. Webb detected the water plume spanning an enormous distance from the Moon, dispersing into the surrounding space along Enceladus's orbital path. This finding reinforced Enceladus's status as one of the most interesting places in the solar system for astrobiology research, given that its subsurface ocean is now known to be actively venting material into space, material that future spacecraft could potentially sample without needing to land or drill. So that's what Webb has actually been doing since it began science operations, finding galaxies that challenge our formation models, revealing the hidden interiors of stellar nurseries, beginning to characterize the atmospheres of planets around other stars, and discovering new details about objects right here in our own solar system. In less than 3 years of operation, it has already produced findings that are reshaping research programs across multiple fields of astronomy simultaneously. But almost since the first images were released, a parallel conversation has been growing online. Claims that the images are computer-generated composites rather than real photographs, that what Webb is actually finding is being suppressed or misrepresented, and theories about what's really out there that NASA isn't sharing with the public. In our next episode, we're getting into all of those claims and examining each one carefully against what's actually known about how Webb works and what it's actually producing. Stick around for that one. Like, subscribe and hype the video so you don't miss part 2, and let me know in the comments which Webb discovery you find most significant. I'll see you in the next one.